Okay, um, this is a addition to the beginning, which I had missed in the actual original lecture. So there'll be a few pages that we'll have to reproduce. Anyway, we're only going to be talking about various kinds of communication systems, one way or the other, and starting a bit with some of the material we had previously done about information theory. So we've talked about the abstract. I won't follow with that. This is 9. And we're going to start talking a little bit about Boolean logic. George Boole developed it. The principles of logical thinking, as opposed to intuition or religious doctrine. At the time in the 1800s, early 1800s, religious doctrine was actually assumed to be the proper way of thinking about things. And we've used logical thinking since the Hellenic era. And Boole's contribution was to show how to systemize these principles and express them in equations, Boolean logic or Boolean algebra. So just as for Matt, no, who was it? Oh, can't think of Cart. Anyway, the guy who did Cartesian algebra or analytic geometry, algebra is the way of using geometry or Boolean logic. So that is one of the primary things that we found over the years, that to use algebra for various kinds of mathematical objects has been a great insight. Boole was the son of a cobbler, and he was more interested in mathematics and optics than cobbling. He built up in Lincoln, England, approximately 120 miles north of London. That's a picture of George Boole, obtained from Wikimedia. And this is also obtained picture of Claude Shannon. This is also from Wikimedia. Claude Shannon, who was born in 1916 and lived until 2001, showed how to use Boolean algebra as the basis for switching technology. His contribution systemized logical thinking for computers and communication systems, both for the design and programming of the systems and their applications. Logic continues to be abused in politics, religion, and most non-scientific areas. But the most amazing thing that Claude Shannon created was information theory. For a few years, it was just a beautiful and fascinating theory. But soon it became the conceptual architecture of virtually all commercial communication systems. Claude Shannon gave a talk that he had entitled Creative Thinking in 1952 to a group of researchers. And he started with three main attributes: training and experience, intelligence, and motivation. The inner drive to formulate questions and find answers. Curiosity about fundamental characteristics. The need to understand in multiple ways, and satisfaction from understanding. Shannon in this talk gave a number of tricks that he often useful, and which appear to be major principles of theoretical research. One was simplification. Get rid of enough detail, as all practical aspects, for intuitive understanding. Similarity to a known problem. Experience helps. Reformulate. Avoid getting in a rut. Generalize more than the opposite of simplify. And structural analysis. Break the problem into pieces. And lastly, inversion. Walk backward. Work back from the desired result. Other tricks that Shannon often used are on the next page. Be interested in several interesting problems at all times. Work on the most interesting one. Look for contradictions as well as proofs. Study what's happening in multiple fields, but don't work on what many others are working on. Ask conceptual questions about everyday things. Don't write papers unless you really, really want to share something fascinating. And don't assure your readers know everything you know. Spoon feeding is not a bad idea. So in his groundbreaking paper in 1948, Shannon said this: the fundamental problem of communication is that of reproducing at one point, either exactly or approximately, a message selected at another point. Frequently, the messages have meaning. That is, they refer to or are correlated according to some system with certain physical or conceptual entities. These semantic aspects of communication are irrelevant to the engineering problem. The significant aspect is that the actual message is one selected from a set of possible messages. And the system must be designed to operate for each and every possible selection, not just the one that will actually be chosen and sent, since this is unknown at the time of the design. So in his, originally his paper, I forget which figure number this was, but I think it was the first one actually. A communication system is a system that is essentially shown here in figure 3. It's got 5 parts. You have the information source. These are the collection of messages that could possibly be transmitted. There's the transmitter. This is some type of a device that takes a message transmits it into a signal. Now, the signal could be many different things. It could be a radio wave, a light, it could be sound, it could be the printed page on paper. There's many, many things that could be a signal. When you use a signal, it will almost always have noise. If it's a paper printed version, there'll be typos, which you've seen I do many of. And if they're radio waves, there'll be other kinds of noise. There'll be all kinds of noise added to any signal. That signal will eventually receive to the other device, which is a receiver. The receiver essentially inverts the results of a transmitter. So the transmitter takes a message, sends it out along a signal. The signal is received. The receiver deducts what from it gets of the signal, what the message is. You take the received message and send it to the destination, potentially and probably some kind of person to read it. Now, in all of this, obviously, or maybe not obviously, but it should be obvious by now, the meaning of the message is not part of the information being transmitted. It is simply a set of symbols in the form of the information source. It gets transmitted and received, and the message that is created from the received signal is sent on to the message. Some messages will be trivial and not have much meaning at all, and others will have great significance. So, the information source produces a message or a sequence of messages to be communicated to the receiving terminal. The message could be any of the following various forms: a sequence of letters, as in a telegraph or teletype system; could be a single function of time, as in radio or telephony; a function of time and other variables, as in black and white television. Here, the message might be thought of as a function x and y of two space coordinates and time, and the intensity of the point xy and t on the pickup at a tooth plate. Very simple way of thinking about what exactly a TV is. So several functions of several variables are needed in color television. The message consists of a F, G, and H, each of those positions and time, and defined in a three-dimensional continuum. And you could think of these three components of a vector field defined in the region. Similarly, several black and white television sources would produce messages consisting of a number of functions of three variables. If those systems are to be sent together, they have to be multiplexed. an analog or digital signal that is combined into a shared medium. And those three functions would be the red, green, and blue of the color image being sent. So various combinations could also occur. For example, in television with an associated audio channel, you have another function of time, but not in addition to either the one black and white signal or the three RG and B signal. So a transmitter operates on the message in some way to produce a signal suitable for transmission over the channel. In telephony, this operation consists of changing sound pressures into proportional electronic currents. In telegraphy, we have an encoding operation which produces a sequence of dots and dashes and spaces on the channel corresponding to the message. In a multiplex PCM, PCM stands for pulse code modulation, the first type of digitation, the first type of making digital signals used for a telephone. In a PCM stream, the amplitude of the analog symbol is sampled regularly at a uniform interval. And each sample is quantized to the nearest value within a range of digital steps. So this is the PCM model. The PCM approximates, in this case, 7.5 times 1 plus sine of 2 pi over 32. And we have 0 through 15, that is 4 bits as a possible set of length. In this case, so you start at 0, and then you're going to go to 1, and then you're going to go, I'm sorry, to 8, and then 9, and then 10, and then you go all the way up to 12 and 13. So you keep finding the closest number to the signal you're sending, and you discretize that into the number of steps that you have, and then you wait until the signal comes to the next result after a fixed amount of time, and you repeat the process. So that's the PCM process. The channel is merely the medium used to transmit the signal from the transmitter to the receiver. It could be a pair of wires, it could be a coaxial cable, band of radio frequencies, a beam of light, etc. During transmission or at one of the terminals, the signal may be perturbed by noise. This is indicated schematically in Figure 3 by the noise source acting on the transmitted signal to produce the received signal. So this part here is where we pick up the original lecture when I had noticed that even though I had it to do a record, it didn't go, and I had to pick it up here. So we're going to quit now. Pressed it, it didn't start. At the very beginning, I had pressed the button to start the record, and I didn't look at the fact that it actually had started. So I'd obviously missed the button when I did it at the time. I apologize.
I have a question.
Yeah.
It deals with the margin of error and how serious that is. You're saying that the transmission is, the goal is exact transmission, but the reality is approximate transmission. So that brings in an error factor. So if the a message is sent from the transmitter and received slightly differently at the receiver, how does that affect I mean, I can think of all kinds of things where even a slight error can be serious.
Yeah, well, that is why I wanted to get to codes, because you can use, everybody knows that this is a problem. So if you just use a signal like a teletype, there's no, the coding is just, a character, and the assumption in the design of the channel is that it's sufficiently strong that you're not going to lose any bits. But that's, of course, never true. And when one of the bits goes wrong, you get a different symbol. So when we get to coding next week, there are various kinds of codes that have been developed, but the Hamming code is the one that's most people try to use there, and you can design them to correct any 1-bit error, or you can make longer codes, and at some point they allow you to do 2-bit correction, and you can do even further for 3-bit correction. So that's what we're going to talk about next week, because that's that's obviously very important. So
Bob, I have a question. Bob, you're kind of mixing analog with digital, and it's a little confusing. It could be confusing to people, but isn't Shannon all about, let's say, digital communications, where you quantize an analog signal and then forget about the analog signal?
No, that's not true.
Okay, good.
The PCM system was done over analog wires.
Oh, of course, yeah, but I'm talking modern digital communications.
Well, I'm not. I'm talking about.
All right, okay, I'm sorry. The other thing is the inaccuracy in your quantization is quantizing noise. It ends up as a noise signal, if you will. It's one way of looking at the way I look at it.
Well,
so you get signal to noise ratio when you reformulate your original signal.
Well, that depends upon the degree of the bandwidth of the signal you're sending. The message, such as the sine wave that I showed previously here, you're absolutely right that, of course, you're getting a step function, the green step function that is shown here. So in that sense, there's error. However, if you have a high enough degree of steps between the highest and lowest, if you have enough bits to be able to sample, and you know the maximum frequency of the signal, then you can reproduce the original signal exactly, because the original signal is bandwidth limited, and there is a whole way of creating signals from samples using if you sufficiently fast sample and with sufficient accuracy, then you can reproduce the original bandwidth signal exactly. And the way I've described it, yes, that's certainly true. But if you had a much higher discretization, you could reproduce that sine wave exactly using bandwidth interpolation problems.
So I used to explain and illustrate the signal to noise problem by giving my students a bag of mixed coins. So every student had exactly the same number of coins, you know, dimes, nickels, quarters, pennies. And I would give them about, a short amount of time to count the coins in the bag. Very high signal, right? I mean, you count a coin, you touch it, you look at it, you turn it, put it down. Turns out that, of course, about 10% of the students got the number wrong. So it says that really not very practical to assume there's never any noise. There's always noise in any kind of system that's at all complex, and it's not the most trivial. And by giving them a short time, I prevented them from encoding the system. You know, when you count coins, you sort them, you stack them. Those are ways of basically doing error correction. So by giving them a short time, they had no opportunity to do error correction. They just got one chance to count each coin, and they, you know, it just a significant percentage of them never got the right number.
Oh yeah. Well, that's the reason why codes have been set up like the Hamming code to be able to have a number of bits error in the symbol being sent, so that error correction is designed as part of the channel. So you can make designs where any one bit error can be corrected. You can design codes where any 2 bits are corrected, where any 3 bits are corrected. So, you know, if you have enough time and you have enough error correction built into the signal, then that goes away. But you're right, if you don't have the time, you don't have the error correction built into the signal, you're going to have noise that you can't just necessarily understand is happening. So absolutely correct. Okay. The receiver performs, I did do the channel. Yeah. The channel is simply the medium to transmit the signal from transmitter to receiver. Could be a whole bunch of things. Yes, I talked about this. But, the receiver is ordinarily the inverse operation of what's done by the transmitter. So reconstructing the original symbol or message from the signal sent to the receiver. And the destination is a person or thing for whom the message is intended. So it could be a person at the end of a telephone call, it could be the screen image on a television, many different things. Communication systems involve certain general problems. We represent the various elements involved as mathematical entities. So in order to understand how you actually do science, you use mathematics. And it's suitably idealized from their physical counterpart. So there's some simplification that goes in terms of the mathematics. And I can roughly classify communication systems into three categories: discrete, continuous, and mixed. By a discrete system, I want to describe a system where both the message and the signal are a sequence of discrete symbols. So this is where it might be a sequence of letters or a sequence of dots and dashes and spaces, whatever sequence of discrete symbols. A continuous system is one in which the message and signal are both treated as continuous functions: radio, telephony, television. A mixed system is obviously one that has both discrete and continuous variables here. During the communication process, the receiver, Bob or B, learns the value of the output. We're continuing our pair of senders, Alice and Bob. And so Alice sends a symbol A, and it's transmitted through a communication process. The receiver, Bob's ears, learns the value of the output. And this is the signal that Bob thinks he heard, not the signal that Alice sent. It's important to understand that because of the party noise that's going on, what Bob hears, he might, be 90% sure that Alice said yes, but there's a 10% chance that because of the noise, she said no. So Bob gains an amount of information, the entropy of the output B. And that still leaves something left over: the information that the receiver lacks about, even though B knows all about B. So this is what's called the conditional entropy. This is the entropy of A given B. And this is how much information the receiver does not learn about the transmitted message. It's a measure of failure to communicate. Is this all clear? Any questions?
What do you mean by value of the output?
Well, we had a 1-bit signal in symbol. Alice either said yes or no. And
okay.
Bob thought he heard a yes, but he's not sure. He's only 90% sure. He's a Bayesian, so he initially thought it was 50-50. After he received the information from Alice's signal, her speaking yes or no, he updates his probability. His probability is now 90%. So based on that 90%, he's pretty sure about a half a bit might be wrong. And half a bit is he's right. So is that clear?
Try to think about that one.
Well,
No, that's right. That's right. Yeah, I know what you're saying. I just have tried to digest that.
okay.
So Bob, if I could ask you the following to numerically quantify this lack of information, you would put these probabilities into the formula for the entropy. So minus
Right, we're going to get there.
log
We're
P.
going to do that.
All right.
Yep. Great. Thank you for shilling for me.
In what you described, is there a difference between lack of information and misinformation?
The way we typically use it, disinformation is where the signal sent, the message sent, is inaccurate. So the starting place, the message being sent, is on purpose sends the wrong message. So that's typically the way the word disinformation is meant.
I didn't say disinformation. I said misinformation, starting with the letter M.
Oh, I'm sorry. I have very bad hearing, and I can't tell all of the consonants. That
You dropped a bit.
yeah, right. I do that all the time. My range of hearing only goes from about 100 to 4,000 cycles. So I'm seriously missing a lot of information because almost all of the information is in the consonants, and consonants start around 7,000 to 9,000 cycles and go up. So the hearing aids that I have actually pick up that signal and then distort them by down frequency, literally translating the frequencies down to the region that I can hear. But of course, I'm getting closer and closer. Once I get to between 3 and 3.5 thousand cycles, I won't be able to hear anything but the vowels, and having them downward translated will not help. So, sorry, I apologize. That's much more information than you need to know. Sorry.
I thought it was
apologize.
interesting.
Yeah.
I thought the diversion was interesting. One way or another, what I'm trying to do is compare no information versus incorrect information.
Okay, well, no information means that you have probability 0 that you got the.
No, I don't mean the entire transmission. I mean the part that didn't come through. What you're calling lack of information.
Yeah, but we're talking here about a single bit. We're talking about a question.
Yes.
Yes or no. So you can lose part of it because you can get the information and believe that you got the right answer, but only with a probability that is less than 1. If you know that you got the correct answer, then you have to update so that the probability is 1. And that's got no misinformation in it, no lack of information in it whatsoever. If you know exactly what has been sent. So the misinformation or lack of information is based on the fact that you don't know exactly what the signal was that was sent. You have you've gotten some information, you've updated your probabilities from the initial ones, and in this case, Bob was, believed 1/2 probability that it was point it was 1 bit of error. There was 1/2 probability of yes and 1/2 probability of of no. Once he received the signal, he updated his probabilities and said, oh, it's about 0.9 that it is a yes, and 0.1 that it was a no. And that is about 1/2 a bit when you run through the numbers through the entropy. So he had 1 bit of uncertainty. Now he has 1/2 bit of uncertainty after he's received the message that he did. Is that pretty clear?
I guess so.
Okay. Information theorists often call the conditional entropy the equivocation of the message. It tells us how much B isn't sure about A, how much he doesn't know about what Alice sent. Even when he's absolutely sure what he thought he knew. That is, he heard something and he knows exactly what he thought he heard, but he has uncertainty about how to use that information to know what Alice sent. They're not identical. They're not isomorphic. They're not one-to-one and onto. There's only an updating of his probabilities, and before they were 1/2, now they're 0.9, 0.1. So a more positive measure is the amount of information that B actually does gain. And the difference is called the mutual information, symbol I of B colon A, and it's the entropy of Bob's receiving message minus the conditional entropy, the message he thinks A is given B. And the mutual, there's a lot of stuff going on, what I've been showing, so we're going to try another picture. So there's lots of different entropies that are going on here. There's the joint entry between the message Bob received and the signal, the message Alice sent. That is actually the whole picture here. And there's various pieces of it. There is the entropy, the uncertainty about Alice's signal, because she may not actually be perfectly certain about what she's saying. So that's the entropy of Alice's signal or symbol. There is, of course, the entropy here, this one, that is the entropy about Bob's symbol that he heard. There is the mutual information, which is the 2 components. So the mutual information of Bob's signal given A. There is the conditional entropy, which is Alice's uncertainty or surprise, given that B got his signal, and the reverse, which is the entropy of Bob's reception given what Alice actually sent. So to understand the whole thing, you have to think about it in this cluster of various components. So this is the overall joint entropy. This is the entropy of Alice's message. This is the entropy of Bob's message. And then this is the mutual information. This is the entropy of Alice's signal, given that B received what he received. And this is the entropy of Bob's signal, given that A is what Alice sent. So there's all these different types of entropy, but they're all very important.
Bob?
Yeah?
Well, I just see by the next text you might be explaining what I'm asking, and that is, I'm still not quite sure what H of A is.
Well, if the answer that Alice sent was without any uncertainty, then this would be actually 0, because she has certainty, probability 1, of her signal being sent.
So in other words, I'm thinking about the information chain that you showed earlier, and I'm wondering what part of that chain would be represented by H of A. Is it?
This
I
one?
guess, yeah.
Okay. So Alice has a collection of possibilities, yes and no. She chooses a message. This message she may be an expert and she knows exactly what the truth is, and therefore her probability is 1 for the message she's sending. Then there's the transmitter. Even if she is perfectly certain and her entropy is 0 because she's certain, then the transmitter, the way in which her signal is sent, may have some error in it. So she may have she might have been from the South and she has a different accent. She might have, her original language might have been Hungarian.
Yeah, right.
So
now,
the transmitter might have some uncertainty of the signal being sent. This is her evocation or her vocal transmission. So there may be uncertainty because of the way in which she speaks. All of this would be H of A, Alice's message.
So H of A would also include, if I understand what you're saying correctly, the fact that Alice herself may not know exactly whether it's a yes or a no.
Absolutely.
Okay.
Absolutely. Great. Thank you. I love it when people shill for me. Okay. So the diagram shows 2 overlapping circles like a Venn diagram. It's not accurate because it depends upon what the various probabilities of each one is, etc. But this is can't think of what the term is for the type of picture I'm I'm drawing that shows the essential factors in it, but not quantitatively, only, anyway, hopefully people understand what I'm saying. Okay. Well,
Bob,
let's start.
Bob,
Yeah.
I have a question.
Yeah.
Would H of A increase if there was more information, or would it increase if there was less information?
Well, for a 1-bit sample, we'll get to a picture here in a while. If you are perfectly, if you're complete, let's see, if you have no knowledge, then the entropy is 0. If you're perfectly certain, if you know exactly that it's probability 1, then the entropy is also 0. And assuming here we're talking about a yes/no question. So the place where you maximize.
I'm worried about your first statement. If the entropy, if the knowledge is 0, wouldn't that maximize the entropy?
No, I'll show you a picture in a while, but think about it. What is the entropy? It's the log of P plus 1 minus P log of 1 minus P. So if P is 0, the first one is 0, and the second one, log of 1 minus 0 is log of 1, which is also 0. So the total entropy is 0. If it's 1, the same logic, but reversed, shows that in both cases, it's also 0. So either perfect certainty or perfect uncertainty, complete uncertainty, has entropy of 0. But at P equals 1/2, that's where it maximizes.
Well, wouldn't complete uncertainty require that if you're talking about a binary piece of information, then complete uncertainty would suggest that the probabilities would be 1/2.
No,
it could be either one or the other.
Well, that's the maximum entropy value. But if you do not know what the answer is, not that you're uncertain about it, you're sure you think it, you don't know it, as opposed to it's equally likely that it could be the other. The difference is between,
well, Bob, you can't.
I know that I don't know anything.
Well, you
okay?
can't have the probabilities adding up to 0. They have to add up to 1.
Well, but the entropy is P log P plus 1 minus P log 1 minus P.
Yeah, but those P's can't be all 0.
Yes, they can.
I thought you had to normalize probabilities to 1.
They do. 0 plus 1 is 1.
No, I mean, the probabilities of an event, a yes or a no, you've got 2 probabilities. The probability that the signal is yes, and the probability that the signal is no. Now, those 2 probabilities have to add up to 1.
Right. And so if I know for sure that the answer is not yes, but no, that gives you entropy of 0. That's what I'm saying.
Yeah, that's complete knowledge. Now, if you don't know anything, the probabilities still have to add up to 1. But each.
Oh yeah, if you're all right. So maybe I misspoke, but if you're certain that it is yes or you're certain it is no, either way, the entropy is 0.
Yeah.
And in between any probability, it goes up and it maximizes at P equals 1/2. We'll see that in a picture in a few minutes.
Okay, we agree there.
Okay. Sorry if I misspoke.
What I don't understand is what is the relevance of whether Alice knows everything or knows nothing in the transmission, in the communication. She's got two choices, yes or no, to communicate.
Right.
So what is the difference with all of her misgivings in between yes or no? She either transmits yes or no, and that's what Bob receives with a certain degree of certainty.
Yes,
So I don't
but
understand.
she may not. I mean, she could be guessing.
So,
She could not know yes or no at all. She could have probability 1/2 and probability 1/2.
but
And
that
she
isn't allowed
quits.
in the transmission problem that you've just set up.
Sure it is. Why not?
Well, how it's what?
Why not?
Well, you've
There's
just given
nothing
two.
that says that the message she's sending is accurate. She's only sending a message.
So what you're saying is if she sends yes, that could mean many things. Yes with complete certainty, yes with partial certainty, yes with 75%, 50%, 25% certainty.
That's why it's a circle, because H of A, she may have some uncertainty about what the message is she's sending.
Let's say the question between the two of them is, will it rain tomorrow? And her ability is to answer either yes or no. And she doesn't, she may think it might, or, if you make it concrete, that may make more sense. So if the question Bob asked her, will it rain tomorrow? And she's got to answer either yes or no, that instead of maybe, because she's only got this, one flag she can raise or lower, that response will bear some level of uncertainty.
Great, thank you.
I think, Bob, what's confusing is up until this point, all of the discussion was about a message emanating from Alice to Bob. There wasn't really any discussion in the Shannon text you created about her intent, her answering a question, all of those things, which I'm not saying aren't interesting and quantifiable, but by making H of A anything except certain, you brought in a whole nother scenario that we've never discussed before.
I know, that's why I'm redoing it over again, because I started with a simplification that made it easier to understand what was going on. And now I'm trying to do it with complete accuracy. But you're right, I started out not saying that she could have uncertainty or that there would be entropy about her message, but in any kind of real system, there's always uncertainty, as most philosophers aren't sure that they're there. So, there's no certainty that you exist. So what do we have to have uncertainty about everything, including the message that she sends.
Okay.
So this is the uncertainty that Alice sent, and it might be certain, in which case the size of this circle would be 0, but it might, she might be 0.9% sure, she might be 0.99% sure, but for some reason she's, if she's got some uncertainty, there will be some entropy. And because of noise and because of possibly as I said, also, even if she is certain, the fact that she has an accent might disturb what her message is being sent. So her whole system of how she creates the symbol to be sent will have some entropy about it. Is that fairly clear?
Yeah.
So, as I said, it looks like there are two overlapping circles, like a Venn diagram. This is not really a Venn diagram, but it's just a picture that shows the relationship between the different pieces. The left circle represents the entropy, the amount of surprise about the message that was sent by Alice. So, if she said it in Hungarian or in Japanese, she might have responded and said hi rather than yes. And so there would be some uncertainty about what she meant when instead of saying yes, she said hi, which is Japanese for yes. And in Japanese in particular, yes has almost no information in it. It is used universally as an acknowledgement, but not does not tell you the accuracy of what's being said by the culture of the Japanese. So there's many reasons why there may be entropy about the signal being sent. So,
Bob, is there some reason you used a capital B here instead of a lowercase b for the right circle? You have H, no, in the next slide. Oh, maybe you have H capital B.
yeah, that's a mistake. That's supposed to be a
okay.
lowercase b. So the uncertainty about Alice's symbol being sent is H of A, and it is the amount of information in the input. The amount, this is H of small b, the amount of information received in the output. The whole area is the joint. This part, all of it together, that's H of BA.
Now we have to think a little non-intuitively, given the way you're expressing that. In other words, the amount of information, if you represent that by a circle, the smaller the circle, the more information. Is that correct? And if the circle has 0 radius, that means that there's no
correct. Correct. That's what I tried to say a little bit ago, that if it was certain that that circle wouldn't be there.
Yeah.
Because it would have shrunk to 0.
So the smaller H of A is, the more information is in the input.
Yeah.
Okay.
I just made these equal because, in point of fact, in the general case, you don't know how much uncertainty there is in the signal being sent. You don't know how much uncertainty there is in the signal being received. So I just made them, maximal and equivalent, but they could be different sizes.
Well, that, and just the idea that the more information in the input, for example, the smaller, not the larger, H of A is.
Yes.
Okay.
So, Bob, is the following scenario equivalent to the situation you're describing? So the scenario says, by prior agreement, A and B agree to send the same signal 10 times. So A Alice is supposed to repeat her answer 10 times. Yes, 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 10 times. B listens, and maybe he hears, because of noise and other things, 10 yeses. Maybe he hears fewer, maybe he hears all no's. Maybe he hears nothing for some of those intervals. On the other hand, Alice sometimes transmits 10 yeses, but gets a little confused sometimes along the way, and maybe will stick in a no here and there. So that sort of represents her uncertainty of the message she's trying to send. So we can divide up in that scenario. We can say if she sends 10 yeses, she actually meant yes 100% of the time. But if she said 5 yeses and 5 nos, that represents the uncertainty and the lack of information in her message to Bob. He may hear more yeses than nos, even though she sent exactly 5 yeses and 5 nos, and she might have intended to send all yeses.
That is certainly one way, but the more general case is just that she may have uncertainty about what the symbol is that she's sending. If people don't, answer unless they're like me, yes with probability 0.9. If you did, you'd know about the entropy rather than just the symbol. But like I say, most people don't do that. So you could just do it, she may think she knows what the answer is, but is not certain. And she gives the best guess she has, the 90%, and sends that off. She has to send one answer, one bit. Okay, so the whole area that I've pointed out already is the whole thing, H of BA, and actually this should be minus, here what I'm trying to say is that H of A plus H of B minus the mutual information is what the joint information is, because the mutual information gets counted twice in the Venn diagram kind of idea. So the language here is incorrect, and allow me to change that later.
Bob, can I ask one other quick question?
Yeah.
You've used a word, when you say at the second line here, this circle HA represents the amount of information in the input, but you've also said it's the amount of uncertainty in the input.
The entropy is whenever you have a signal you're sending out, there's a probability between 0 and 1 on the signal that you're sending. And of course, the opposite of it would be 1 minus that. So the total entropy is always P log P plus 1 minus P log 1 minus P. So so you always need to know the uncertainty about both the signal sent and the uncertainty of the signal sent, because it could have some other value.
Okay, it's just the words information and uncertainty. I've just got it. I know those two words, but just how it's stated here, I'm still confused. But that's okay, no problem. I'll deal with it.
Well, the amount of information is the average amount of surprise, which is the entropy, the P log P plus 1 minus P log 1 minus P.
Okay.
Could I clarify something?
Sure.
Bob what Bob receives, he never knows where the uncertainty is coming from. It could be coming from Alice, or it could be coming from the fallibility of the transmission.
Right. And he has his own original probabilities of what the answer she's going to send is. We've assumed it here that he is completely uncertain. That is probability 1/2 of yes and 1/2 of no. But so there's his original uncertainty, and then the entropy he gets is after he gets the signal, he has to update that probability, and that gives his conditional entropy. So you use Bayes' rule, and you get a signal, you update it, and the conditional entropy is the probability of that updated probability.
Okay.
Whatever the uncertainty is about, whether it's about the fact that you had uncertainty to start with, if it's due to the fact that there was signal wrong, if there was uncertainty, you know, for any reason,
Yeah.
you have to update the probabilities and calculate those updated
Okay.
probabilities. Okay. So the overlap of the two circles is the mutual information. That is the B information that is also A information. So the amount of the output of the channel tells us about the information. That's what the mutual information tells you. It's the amount of entropy that is also part of, it's part of the B information that is also part of the A information. And it's the amount of that the output of the channel tells us about the input. So it's in a sense how much certainty Bob understands what Alice knew about and sent. So the amount that the output of the channel that's what it is, the amount of output the channel tells us about the input. Okay, so let's see if we can stop being abstract concepts and hopefully move on to a simple example to make it more clear. We've assumed that the input A is a bit, a yes or no, or 1 or 0, and from Bob's point of view, equally likelihood, 1/2 probability of each one. The output is this, I'm sorry, the original collection of messages are equally likely. And then Alice chooses one. And the output is also a bit, a 0 or 1 or a yes or a no. And the output may or may not agree with the symbol that Alice chose and sent. The bit might flip, change the opposite value along the way. So let's say that the probability of an error is the symbol E. So here's a diagram. You have what's called a symmetric channel. It's symmetric because the probability of either 0 or 1 in the collection of symbols originally that both Alice and Bob are trying to communicate about. Those were, the probability of those initially were assumed to be 0 and 1. And there could be a flip. So you could have a 0, instead of going to 0, it could go to 1. The probability of that is E. If it was a 1, it could flip to a 0. That's also got a probability. That also has a probability of E. For a 0 going to a 0, of course, which is what you're hoping for, has a probability of 1 minus E. And a 1 going to 1 has a probability also of 1 minus E. Okay? So this is a symmetric channel with an error of flipping a bit equally in both directions, either 0 to 1 or 1 to 0, with probability E. Is that all clear?
Yes.
So the probability that the input 0 will yield the output 0, that is, the probability of 0 goes to 0 is 1 minus E, as I showed. And the probability that the input 0 will yield a 1 is E, as I showed in the diagram. So this is why it's called the binary symmetric channel. The binary because its inputs are just binary digits, symmetric because the probability of error is the same on both directions. This is just like our example of Alice and Bob at the noisy party. Alice's yes or no is what she says. B is the signal that Bob thinks he hears in the party noise, and possibly her accent or whatever. Anyway, this might be the same or not. And so the probability of hearing the signal A sent is incorrect is E. So the error probability is E. So what about the entropies? The entropy, the input is 1 bit. And so H of B, the entropy of the output, is also potentially 1 bit, but the joint entropy of the input and output is a little trickier to calculate. So let's first write down a table of the joint probabilities. So the joint probabilities, Alice, we're assuming here she, in fact, was perfectly certain of whichever signal she chose. So all of the error is in the channel. This is a channel error. And so the probability that goes from 0 to 0 is 1 minus E over 2. And the probability that goes from 0 to 1 is E over 2. And the probability for a 1 is the reverse of the other 2. When you work out what the joint entropy of the signal sent by A and B. It's 1 plus the entropy of E and 1 minus E. So this is the entropy. When you work all this out, it turns out to have just the entropy. And usually this is just shown as entropy H of E, but I added the 1 minus E because most people don't remember that the entropy is P log P, or E log E, plus 1 minus E quantity times log of 1 minus E. So I added the second part of the probability just to make sure people remembered that. So the joint probability is 1 plus the entropy of E. So let's see, I think I talked all about this. So we have P equals E, Q equals 1 minus E, H of P and Q, P log P plus Q log Q, where P is E and Q is 1 minus E. So if you look at the entropy of H of E, this is not H of AB, this is the entropy of the error in the channel. And if you're exactly certain, again, 0 log 0 is 0, and Q is 1 minus 0, or 1. So you get 1 log 1, so you get 0. At the opposite end, with perfect error, where the uniformly, every time you send a bit, the opposite bit will be sent. That is the nature of the channel. So at that end, P is 1, so 1 log 1 is 0. 1 minus 1 is 0, so 0 log 0 is also 0. So either at 0 or 1, you've got entropy of 0. And at 0.5, you get the maximum entropy, which is 1 bit. And that is where you get 1/2 log 1/2 plus 1/2 log 1/2. And that turns out to be 1, which is the number of bits. Everybody clear?
So,
Pardon?
I agree with the graph, but if you go back 1, I don't quite understand the joint probabilities. Could you go back 1 slide?
Okay, the joint probability
to
is
the
1
table
plus
that you
this 1.
No, one more. There we go. So if I add the probabilities of a row, I get 1/2. So that means that Alice has a 50% probability of sending a 0 or a 1. But if it's just the channel issue, she has made a decision what to send, a 0 or a 1. So why isn't the sum of the probabilities of a row 1? She sends a 0 with probability 1, or she sends a 1 with probability 1.
But that's not the probability of this symbol. It's the probability of this symbol given her choice. So that's the the conditional entropy.
So this is the idea that she may intend to send a 0, but there's a 50% chance she actually sends a 1.
Yeah, we said the original collection of bits, the symbols that make the whole system work, were equally likely, half for a 0 and a half for a 1. She may have other additional information that she uses from those, but the symbols that she's using from are equally likely to be put into the channel.
Thank you.
I didn't understand something you said. It was something to the effect of every time one is sent, then the opposite one is sent.
Yeah, that's the.
I didn't understand what that means.
Well, the opposite one is received.
Yeah, so if the probability E was 1, then the error is such that whenever you send a 0, you're trying to send a 0, Bob will, with certainty, because the channel has error 1, will have 0 chance of receiving what is sent, and instead will receive a 1. So when the error is 100%, you're flipping the whatever is sent, you're flipping it with 100% chance. Did that make sense?
I understand that part. Then what's the part about sending the opposite? That's so that it'll flip back?
Well, if the error is 0, then you're going to be sending the exact information with perfect fidelity. So the two are symmetric. You either have a probability, if there's 0 or 1, the opposite, the extremes, then either the symbol will always flip or it will always send exactly the right answer. So there will be no, if it's 0 or 1, either way, there will be a perfect transmission or a exactly opposite transmission.
Oh, okay, that makes sense. However, I mean, how does the sender know?
They don't. It's the channel is a system that, you know, if you were doing the telephone game that we talked about last time, and somebody is being perverse, so somebody starts the message, says yes, the next person hears it's yes and says no to the next person. So, and if they say no, they say yes. So it's just a matter of how the channel works. In the telephone game, there's a series of people that get the messages and sent them on. And there could be somebody who just, you know, with perverseness or whatever reason, always gives you the opposite answer. So, and the channel could be anywhere from 0 to 1. And at the two extremes, you're either getting perfect fidelity or perfect anti-fidelity.
Okay.
Okay. So, and at the probability of 0.5, that's where you have 1 bit of error. So it's greatest when p equals 1/2. When the two messages from the binary source are equally likely. In that case, the entropy is 1 bit.
When
Now,
you say the entropy is 1 bit,
yeah, the entropy is also called in bits.
it is, because
Yeah.
it's just a number. I'm not sure where the bit comes in.
It's, well, if they're done in log 2, they're called bits. If they're done in log E, they're called nats.
Okay,
If
I
they're-
got you. All right.
They just have, they have names made up for it.
Yeah, I see.
They don't have any mathematical meaning, and they don't have any physical meaning. They're by convention. Like I say, there's bits, nibbles, gnats. There's a whole bunch of different ones depending upon how you do the nits is base 3, gnats is base E. There's a whole bunch of names that are used for entropy, all by convention and based on the base of the logarithm used. So I didn't make this stuff up. I'm sorry. All I can do is tell you what people do.
I just forgot that convention for a second. That's why I raised the question.
Okay. Well, like I say, thanks for shilling me. These kinds of questions are always very useful. Okay. So in the case of they're equally likely, entropy is 1 bit. The entropy goes from 0 to P is either, and the entropy goes from P either 1 to 0. And in one case, the message 0 is certain. In the other case, the message 1 is certain. But in either case, 0 or 1 probability, there is no surprise. So how about a likely transmission error of 0.9? First of all, you remember this is symmetric. So 0.9 and 0.1 have the same entropy. Okay, 0.2 and 0.8. All of these things, P and 1 minus P for E have the same entropy. So what about 0.9? Well, it's a pretty steep function out here. Here is the error equals 0.9. And if you notice, the point here is at 0.69. It's almost a half a bit, even though you're 90% sure, or 90% in this case, that the error is wrong, it's only lost half a bit. It's at a little bit more than a half a bit. So, and of course on the other side, 0.1 and 0.9, it's got the same one. So the entropy doesn't go down with the error very fast, very quickly. Okay, as I said, they're symmetric. As far as the entropy is concerned, it doesn't matter whether 0 or 1 is a more likely message. So whether it's in the design of what we've been doing, we're assuming it's symmetric, the channel is symmetric, and therefore whether it's more likely or less likely, whether it's a 0 or a 1 doesn't change the result. So if E equals 0.9, we're 90% of the way to 1 minus the value of the entropy. And surprisingly, that is still 0.469 bits, almost a half a bit. So even though you've got pretty certain kinds of channels going through, you have actually quite a bit of uncertainty about the signal that's going through, which is why next week we're going to talk about correcting codes and how those show you how to correct 1 bit, 2 bit, 3 bits, etc. Okay. So now that we've calculated the entropy and the joint entropy, we can fill out the rest of the pieces, and this is unfortunately hard to see. The joint entropy is, as we said, 1 plus the entropy of the error, 1 minus the error. The conditional entropy, I can't even read it here. God, I apologize. I'll have to change this. I'll have to put them as outside and put the symbols here and someplace up there and someplace here. I'll change this picture. This is terrible. This is the one I was working on just as I was starting the lecture, so I didn't see how badly it was. I apologize. So I have 2 questions here. What is the H of A and what is the H of B? And I'm considering that as an exercise for you to do on your own time. And next week I'll have the answers in this slide. That is as far as I got. Like I said, next week we're going to start on codes. This is not everything about channels, but it's the most important part about channel. And I'm going to move on to error correcting codes. There are several other kinds of codes as well, which I'm not going to discuss very much about. I hope that this was somewhat useful, and considering the time, actually it wasn't so bad that I only did this much material this week.
No, very well done. Enjoyed it.
Thank you. Thank you, Bob. It was great.
Bob.
Yeah.
Thanks.
Thank you, Bob.
Bye,
Okay,
everyone.
Everybody stay safe.
Yeah.
stay safe.
See you next
Bob, question, Bob.
Yeah.
I'm sorry,